Yes, Will.
Alright, for mine I chose phone battery against time, and I think my function that I picked in the end was 50 cosine of pi over 6x plus 50, and I collected 4 pieces of data. Hour 0 my phone was at 100, hour 6 my phone was at 0, hour 12 my phone was at 100, and then hour 18 my phone was 0. And you may be wondering why this is sinusoidal and not linear, but it's because I think we've all had those times when we've been playing on our phone for like an hour and it's dropped like 5%. Then you play the next hour and it drops like 20%, the next hour like 40%, and the next hour like another 40%. So we've all had those periods of time where it does not model a linear function. And I noticed this in my life on things such as car trips, where my phone has started to die faster as the battery gets lower, and the consistency that it follows is very consistent. And yeah, I just got the idea when I was looking at my phone in the car one day.
Cool. Questions? I'm kind of wondering the rate at which the battery decreases is the same at which it increases, so it's the same at which you charge it. So like if you think about on the downslope of the sine
It's like a
curve.
trickle charger.
Huh?
It's like a trickle charger.
Okay, alright. Good, that's a good cover up. Sure. That works. What was your period of time?
My period was 12 hours, my vertical shift was 50, amplitude 50, midline 50, minimum 0, maximum 100.
Very cool.
Does it take the full 6 hours to charge?
Yeah.
Really?
Well, if you have the case on it, yeah.
Oh, okay.
So charges about an case.
Yeah.
Gotcha. Alright, who's next? Yeah, go ahead, Jim.
Alright, so I graphed the rotation of the Earth in relation to the Sun and the Moon. So the reason I chose this was because I forgot to bring my watch to the farm because it's my sport one day, and I was really tired and I wanted to leave, so I used the sun to tell what time it was. The rotation of the Earth is constant. It's a sinusoidal graph. Because it's a perfect sine graph, it was used by most cultures in the world to tell time for thousands of years. They had stuff like the sundial and whatever. So my period was 24 hours because a full day. Every 12 hours the sun rises and sets, and at every 12th hour in the day it's either fully up or fully down.
Is it perfectly sinusoidal?
Almost. It depends on whether you're on daylight savings times or not.
Okay, so what might affect it then?
Your rotation around the sun. The position in Earth orbit around the sun.
Right, and if you think about like how the sun rises and sets in the winter versus the
Exactly.
summer.
Yeah.
Right.
So it's not perfectly. It rises at 6 and sets at 6. It's depending on where you are in relation to the sun, it'll change just a little bit.
Absolutely. Any want to have questions on what James did?
What, this might be a bad question, but what if it's like a cloudy day or something? What if there's no sun that day?
But the sun's still there. I mean, the Earth is still orbiting, rotating. It's just you can't see it.
Other questions? Alright. Yeah, go ahead.
Mine relates pretty well to that. So, I chose to do my project on the hours of daylight for a year. So I looked up in Salisbury, Connecticut, right? All the hours, the amount of sunlight for each day in the year, right? And so, I'm a big outdoors person. I love biking, swimming outdoors, all that fun stuff. And so I thought that it would be pretty cool to see when I would be able to get the most use of my time outdoors. And so after using this data, which helped me find my equation, I used Desmos to graph it. And pretty much what I have is, I use minutes, so this relates to the minutes of daylight that one day, right? And this relates to the number of days it is in the year. So, for example, January 21st would be the 21st day, and so on. So, pretty cool. I was thinking one of my ideas is that I should give it or sell it to Hotchkiss, because I think that it would be useful for students.
So yours was, in what ways similar to what James did, in what ways different?
Sure. Similar and different, exactly. So similar in that we are both dealing with the sun, except that for mine was more of a just related to the sun and the amount of daylight, the amount of sunlight that one day. It didn't really have to do. I mean, obviously, I'm sure it does have to do something with the rotational, which is why there is that sinusoidal function, but it's different in another sense.
Absolutely. If you actually look at kind of like a zoomed in version of what you have, it might be sinusoidal kind of going down in terms of the amount of sunlight, which is like, that would be a snapshot of what James did. If you kind of blow out the big picture, you'd see a larger sine curve. Pretty cool.
So I use this app on my phone to model my blood pressure and use it as like the flash camera. And I wanted to see if there's a difference in blood pressure after taking our test, which was somewhat of a stressful environment. And then right after I woke up, which is the least stressful you'll ever be. So I had two different sine functions, and blood pressure varies sinusoidally with heart rate. So when compared with heart rate, over the course of one beat, your blood pressure goes from its highest pressure down to its lower pressure. So I did see different results for the two readings, and I had a much lower blood pressure when I was not taking the test.
Nice. Questions for James?
Wait, so your blood in one beat goes from the pressure from just when you've woken up to the pressure of just after test?
No, in one beat, blood pressure, it's usually expressed one number over another number. So the top number is what's called systolic pressure, and the bottom is diastolic pressure. So it's just the pressure exerted by blood in your blood vessels.
So was your graph blood pressure over time or systolic over diastolic?
It was blood pressure as a function. Pressure, it's like expressed in millimeters of mercury. And get the deal here. Pressure as a function of beats.
So how did the pressure after you've taken the test and after you've just woken up affect your graph?
It was pretty much just a vertical shift.
What was the time frame for how your blood pressure would vary sinusoidally?
So in order to get the period, if we wanted to do pressure as a function of beats, you would have to take into account your heart rate, beats per minute. So you would take the amount of seconds in a minute, 60 seconds, divide that by your heart rate, and then you'd get the period.
So what would change if your heart rate increased?
The period would become smaller.
Cool. Any other questions? All right, Shane.
Okay, so, we talked about like how sound waves were like sine functions. So like I was curious if I play different notes in my violin, will it be same graph or different graphs? So I had to look it up. It's of A string. If you're more familiar with the piano, it's A over the middle C, and E is the E right next to the A higher. So for A, for both A and E, the amplitude was 1 hertz, and then the midline was 0. But the only thing that was different was the period. So I noticed that for A string, it was sine function of 880 pi over x, and then for E string, it was sine over 1,320 pi of x. And then I found out that if the pitch is higher, the period gets smaller. So like it's like 1/440 for one period of A string, and then 1/660 over seconds for D string.
Any questions?
Did you only try the A string and the E string, or did you try different chords for different?
I tried A and E both. Then it was not a sine function, but it was still a periodical function. It kind of looked like the heart, like the blood pressure, but I didn't include because it was not like a sine function. But it was cool.
So you just maybe took a snapshot of the portion that was a sine function, or
I just
did
like,
you omit
if it's
data?
a single note, then it was a sine function.
Okay.
Then if it's a chord like I don't know A, C sharp, and E, then like it was like something like that. But it still had a period, but it was not a perfect sine function.
Okay.
Yeah.
Did you try any other notes?
I did not, but I bet it'll be the same. The period will be.
Is that what? So you
Go ahead.
Is that what they say? A440.
Sorry.
Wait. So what was the for A? What was it?
So that's the period was 1/440. So it's a sound wave, and then the one period for this the period is 1/4.
So like if you held it down forever, if it was forever, right, non-stopping, because wouldn't it stop at some point? Or?
Yeah, I mean, the period is just like if it's 1 second, there are like 440 periods inside.
Okay. Well, that's a lot.
But yeah, so you're just saying it would eventually
Yeah.
taper out, right?
Eventually, right? Yeah.
Did the pressure at which you hit the key affect?
You mean the violin?
Sorry, the violin. How did that affect the period or amplitude?
I don't think it will affect though. Like, or actually, the amplitude might go up. Yeah.
But you think the period?
Yeah, the
would
period will
stay
stay
the
the same because that differs the pitch. And that like yeah.
Cool. Mid-line was said.
Yeah. Of course.
Nice. Who'd like to go next?
I will.
Go ahead.
Alright, so I was having a hard time coming up with an idea, and I was walking after school one day and I saw a tennis ball on the ground, and I started bouncing it, and I found that it bounced sinusoidally. And I figured that since I'm about 6 feet tall, since my arms go a little bit below my waist, if I bounce the ball on the ground and then it goes up to about my head and then I catch it, and I can do that repeatedly without stopping, that would be a sinusoidal graph. So my midline would be 3, my amplitude was 3 feet, my period was 2 seconds, and then there's no shift, and my graph is y equals -3 sine times pi x plus 3. And the reason you'll see a negative coefficient in front of the amplitude is because I wanted my graph to model real life more so than just like a normal sine graph. And since I throw the ball on the ground first, that's why I put the negative coefficient there.
So what was the height at which you started at?
Well, I figured since I'm roughly about 6 feet, and my arms go a little bit below my waist, which is where about 3 feet would be, it would be 3 feet.
Cool. Questions?
The only problem with my thing here is when I catch the ball, there might have been a little bit of time where I held it, so it might not have been just a perfect curve. It might have been a curve and maybe like a second, and then I'd go again. But that'd still be sinusoidal, right? I don't know.
If you omit that.
Yeah. So I omitted that in mine.
If you bounce it harder, won't it go up higher, but like it will stay the same where you catch it. So like it will not be like a perfect balance.
Well, I was just casually walking and bouncing the ball, so it was going about my head level every time.
When we talk about this difference between, modeling something in a perfect math realm and then the difference that takes when you in practice, right? And that's kind of what math deals with a lot. It's just modeling something and trying to get as close to it as you can, because it almost will never match up exactly. Any other questions for Elijah? Alright, who would like to go next? Kat?
So I modeled the temperature of Lake Mount September over the peak months. So I did from April to November in the year 2011 because I found the data on the lake website. And 2011 was the one year that wasn't affected too much by rain or dryness in the lake. So that would have obviously affected the results. And I found that, you know, obviously the lake is going to be colder once the ice melts. So it's cold in April, reaches its peak in August, and then gets colder again in November. And it's probably going to repeat that pattern, you know,